So my name is Daniel Escano. I'm working for the Canal Working Group, Linaro. So this presentation is to introduce a proposal to try to comply with the skin temperature. So before going in the details of the proposal, I have to define some terms and explain what are the goals of the different frameworks. And then I will give a brief description of the thermal framework and show that what kind of real usage we have today, what are the limitations, and what is supposed to solve the proposal. And then I will end up by something open to more work using this proposal. So we can see today that this figure is to show what happens with the temperature on some SoC. Especially here we have a CPU. So please consider that it's for evaluation board. So that's not depending on the form factor, the behavior might be very different. But here we can see that we have two generations between two SoC. The first one is the IKEY, the second one is IKEY 960. And we see for the IKEY 960, which is the green figure, we have we start very compute intensive task, and we can see that temperature is raising immediately because the frequency where the hardware is able to reach are very high. And then we have this sawtooth aspect of the figure, and this is when the system is considering is detecting the temperature is too hot, and then we begin to change the performance state of the CPU, and we see that then the temperature drops, and then as the temperature goes below the threshold, then the temperature increases again, and so on. So we have this sawtooth aspect of this figure. So that's the purpose of showing this figure is showing that the heating effect on the SOC can be very, very fast. So we have in the terminology, we have one term. The term is the junction temperature. So we have to understand that this junction temperature is to protect the silicon. So we define a temperature. So we have different layer of protection for the thermal. We have the kernel side, then we have the firmware side, then we have the hardware side. And we prevent, of course, when we are reaching the firmware or when we are reaching the hardware, usually the critical is just shut down the system. And we don't want to do that for the system because that we can lose information, we can break the system for any reason. So it's bad things to cut immediately the shut down the system. So we try to handle that first from the kernel side, and from that, then we have this result temperature, and the mitigation happens. Then we have the skin temperature. The skin temperature is the resulting temperature on a specific place where it's a place where it's supposed to be in contact with your skin. So if the temperature this temperature must not go beyond the 45 degree, more or less, because if you have something close to your on your skin with a temperature of beyond 50 degree, more than 30 minutes, it results in a first degree burn. So for this reason, there is a form factor, and there is a dissipation. There is the hardware is allowing to dissipate the temperature on the SoC, and that allows to have this skin temperature, even if we have more heating source on the phone, which are much higher than 45. So do we just skip the thermal design power because it does not have interest here? So of course, the SoC during the last years, the SoC increased a lot in terms of density on the component. With the component we have on the board, we have more and more components. The intensity is increasing of this component, and of course, the source of heat are also increasing. And we can find now NPU, we can find a lot of CPUs. They are going faster and faster. The memory also is going very fast. So these are all sources of heat. And of course, we cannot have all of them working at the full performance state at the same time. And we need to have something to prevent that, to mitigate, to have a knowledge of how it behaves the platform, and to say, okay, now I know that this kind of profile will be using more this device than this device. I will decrease the performance of this device instead of this device, and so on. And with that, we ensure that we are still inside the power consumption, which won't increase the temperature increase the temperature, reaching going up beyond this skin temperature. So we end up with some challenging use cases. For example, when you use virtual reality, if you reach the point where you don't mitigate, well, you don't ensure the skin temperature, you don't make sure that you are not distributing the power, the dissipation of the power of the different devices by capping the performance of some devices instead of other. You can reach a point where, for example, it is the thermal framework which is taking control of the mitigation, and it is not taking care of the user experience. It's just trying to save the silicon. So you will cap the performances a lot. It can result in frame dropping, and if you are using virtual reality glasses, then you can feel dizziness. For example, for the gaming, you might have the CPU, because the CPU is the CPU OPP is set by the scheduler, and the scheduler is detecting you are above a certain threshold, then it will increase the OPP. But actually, you don't need to have this OPP, because you can meet the deadline for the computation. And by not but using this OPP, actually, you reach a high temperature, and you propagate also the temperature, the heat to the GPU, and it can result also in a mitigation for nothing. So we have different examples here where if you don't manage correctly the performances of the different devices, you end up by having mitigation, and mitigation means performance drop a lot. I will show that right after. So this is a quick overview of the thermal framework. So actually, it's not very the figure. I should have put the thermal zone figure at the center. The thermal zone is the software component which is aggregating the governor, the sensor, and the cooling devices. The thermal zone are always, basically, I don't want to talk about some specific cases where we have two thermal zones covered by one single cooling device, but usually what we have is a one-to-one relationship. So when you have a sensor, temperature sensor, you can have up to 20, 25 sensors on the SoC. Each sensor is represented by a thermal zone. This thermal zone contains a set of temperature threshold, and when the temperature is going above this threshold, then the governor takes place and choose an action to do. Increase the cooling effect, so it will act on the cooling device, asking for more cooling effect, or it will detect that the temperature is decreasing, the trend is decreasing, then it will ask the cooling device to reduce the cooling effect. there is no communication between the different thermal zones. There is no communication between the different governors. There are not communication between the different cooling devices. They are not aware what's happening on the different places. That means if you have one device heating a lot close to another sensor, and even if the device of the second sensor is not in use, then the heat propagated by the first device can trigger mitigation on the second one. So there is no communication at all. That's the reason why we need something smarter. Then for the cooling device, we have two categories of cooling devices. We have the active cooling device. So these are cooling devices which need energy to cool down, like a fan, for example. And you have the passive cooling devices where we reduce the power consumption. So we don't need energy to cool down. And for that, we have the GPU using def rec and CPU using CPU rec. So we reduce the OPP. When we have a too high OPP, we reduce the OPP. And then we have a specific case also for a CPU in case the CPU rec cannot work, or if the CPU is not DVFS capable, then we can mitigate also with the idle injection by forcing the CPU to do nothing during some amount of time. And that allows the CPU to cool down during this moment. So here we have a figure. The first figure on the top is showing the temperature and the duration of the run. So we run the same compute intensive task we had previously. And the governor for the CPU rec is user space. That means we set the OPP, we change manually the OPP. We do a run and we set at the lowest OPP. Then when it finishes, we set the second OPP, we run again, etc., until we reach the last one. And we can see that the first one is taking a long time, but the temperature is not increasing a lot. While the more we are increasing the frequency, the more the temperature is increasing. And also, the faster is the duration of the computation. But when we reach the last one, the highest OPP, we can see that the duration of the run is as long as the lowest OPP. Why? Because the system, the CPU in this case, is heating so much that it triggers a lot of transition to reduce the power. And in the figure below, what we can see, these are the transition. So we see that the cooling state, so that means we reach at the end, we are doing so many transitions that we don't see the lines. We see just a green square there, a green rectangle. And the cooling state means we are between 2 or 3 OPP below the highest. So here we drop a lot the performances. We are very high in frequency for nothing, and we are losing all the performances in this case. So it would have made more sense to run the same test, the same application, 2 OPP below, and the result would have been better. So in order to prevent this situation, the user space tries to reduce the power consumption, limit the power on the device by using what is exported in sysfs. And what is exported in sysfs is the cooling state of the cooling devices. So there is an abuse of the user space, which is changing this cooling state because it is exported, and regardless any decision from the kernel. So we have conflicting decision. I will just, yeah. So the user space daemon will set some opaque state for these cooling devices. There is no knowledge of the power. So it is actually doing like what is doing the thermal framework, saying, okay, I know that this temperature is more or less this power, then I will be waiting for this temperature, I will read this temperature, and then I will change the performance state by using the cooling device and see what happens with the temperature. So there is opaque values, which are the cooling device state, and they are very platform dependent, because some cooling devices, I saw that some cooling devices have up to 1,000 states, like brightness screen. They put that as a cooling device, so they can act on the power of the devices. So the proposal is to separate clearly by goal what is supposed to do the thermal management, the thermal framework, and what is doing what we are doing when we are doing power limitation. So we say, okay, the kernel-based logic will be handling and protect the silicon by managing the thermal junction, okay? And that will be up to the thermal framework to do that. And the user space will use another interface, which is the power cap framework, to set the power on the different devices in order to achieve this skin temperature. So we have two different frameworks and separated by the main goal they have to achieve. So what is the power capping framework? The power capping framework is an empty shell, is just an API through sysfs, and it's up to someone to write the backend driver to plug that on this framework. So today we have just one backend driver, which is the RAPL register. The RAPL register is a register to do energy limitation, and also it's also energy counter. And by essence, because the power cap is a sysfs directory, we can create the tree of directories. And each directory, which is representing one device, has a set of files where we can read the power consumption, write the power limitation, and set some other options. And because we have this hierarchy, we can rely on that to create the hierarchical constraint on this tree. And there is a library also, a user space library, allowing to directly act on this sysfs, directory structure. So now let's imagine we want to represent that. It does not really, this representation does not represent necessarily the floor plan of different sensor, but it's a way to represent the constraints we want to apply on the system. So if we have here this tree represented, then we can put weights on this tree in order to distribute the energy budget if we decide to assign an energy budget at a higher level of the tree. Today, we have the energy model. Of course, I agree the energy model is not perfect. It might be not the most accurate, but it's not the only thing we have today. And this energy model allows to do an association between the performance state and the power consumption of this performance state. Thanks to that, we should be able, we are able to create devices and export the power consumption given the current performance state and the power associated to this performance state. And also, we are able to limit the power consumption because the framework, the CPU frag framework allows to put constraints on the CPU frag. And in this representation, each node, which are not real devices, are just virtual to aggregate the children and allows to pass the power limitation to the children and aggregate the power characteristic from the children. Thanks to that, the user space doesn't have to act on the power here and there to change the power of the different devices and hack the kernel. They have available one single interface. So if we take an example here for power distribution, let's imagine we have here the weights. We compute the weight given the maximum weight of the maximum power consumer by the big CPU. We have this weight, and the sum of this weight is 1024, which is usually what we do in the kernel to compute percentages. And we decide to set a power limit, for example, to 2,800 milliwatts to that. With the weight, we distribute this power to the different children on the tree. And we have a static limit in milliwatts for those devices. Then we can read what we are actually consuming. And in the case, for example, here in this example, the big CPU is not using all the power budget, all the power we allocated. So we have more than 1,000 milliwatts available, and we can use this available power to the siblings and stay always in this constraint we put on the upper node. So we can dispatch that given the weight again to the other sibling, and that will result in again free power for the other. And now let's imagine the little wanted to have more performance, and then we increase in terms of performance. So the power consumption will increase, and now the big wants also to have more power, and the performance increase. Then it takes more. We are violating this constraint, and now we have to, the big has to take back the power it gave to the other sibling. Then we go back to the dynamic limit. We set the dynamic limit, and we see what is used and unused. So we see now the big is come back it is fulfilling the constraint, and we still have 300. So we can dispatch that. We see there is 200 still free for memory, and we give this 200 to the little again because it needs more power. And at the end, we are still violating. We don't have free power, so the little is above the constraint, beyond the constraint. So we don't have the choice. We limit the power, and we fulfill the constraint. That is the algorithm to automatically balance the power across the different nodes by putting just a constraint on the top level.
Okay, you're almost at the end. That's fine.
Yeah, so we go to the conclusion directly. Yes, for reference, there is a status of the current ongoing work. So as a conclusion of the presentation, we see that we have one framework, which is the thermal framework, and it is abused by the different in-house solution we have here and there, and the solutions are not upstreamable, and it is not the main goal of the thermal framework. The main goal is to protect the silicon, so we want to keep this goal. But we see that the different SoC are getting more and more complex, and we have to manage the power, the heating effect of all these devices as a whole in order to ensure that we keep this skin temperature. And the proposal, our proposal is to create a power cap framework based on the energy model, but it can be extended to more things like the SCMI in order to model the constraints we want to apply to the different devices. But we still delegate the logic to the user space, even if we can have a subset which is able to handle the power balancing on the different nodes. We provide one single unit making sense, which is the watt. And I just skip this section, but the power cap framework allows to create any number of constraints we want. So this solution is extendable, and we can change the semantic of the constraint, like setting, for example, giving some room for the power violation, so before capping, so that we allow some peak load and without doing the limitation. Okay, so that was short. I finish. Thank you. I'm available on the channel if you want to ask any question.